questions during that talk. So again, this is something very basic. We understood and that you have different cultures. That's clear for that for a geochemist. This is something that is quite difficult to understand. And again, I repeat, so if you need specific explanation, we can have meetings after the courses, and we can one by one or a group of people, we can have a discussion of a specific point. So if you need, so keep in mind that the idea is really to train you at a specialized level. So it means that this is important for us to spend time discussing with you about some points. And you saw that in some cases, and maybe I would say many cases, we have no answer. So we can help you to know in which way we can go, but you will see, and this is the reason of this training project, that they have a lot of points that we don't know about. Okay, so now it's time to discuss about the source. So it means the erosional areas. And I will again be back to geological objects, and you will have the theory and the modeling with Seb and Jean. Okay, so this is the point. So as mentioned, Jean, before, there are evidences of submarine erosion. Okay, so it means that it exists. So the most famous example are the submarine canyons or the wave-cut platforms. But I will focus only on the continental words, and you understood that there are mainly four types of words. The first one is all what is related to glacial, peri-glacial environments. And when I talk about peri-glacial, it's what corresponds to the permafrost area. Good example. This is Siberia, so I did not plan to talk about permafrost, but it's something that you have to know about, the way it works. And the second word is the eolian, and there are a lot of features, even erosional in the continental words. Alluvial, no, not problem, and all the question of the soil. And soils are very important things in source-to-sink approaches, because in soils you can generate sediments, okay, and or you can destroy rocks. So it depends. So you have different type of soils, and this is something that you have to know about. It's clear for everyone. Those four main words in terms of continental environments. Okay, so I will start with something basic, and maybe you will say this is obvious, trivial. It's how to identify erosional versus depositional landscape in modern systems. So I just want to make sure that everyone is able on the field, looking at different maps, to be able to say this is depositional, this is erosional. Transfer is quite difficult to look at, but I want that at the first order you're able to do that. So I will leave you a couple of minutes. No, that's not easy because you don't have the documents. So it's where is the limit. So the two documents are on one side, the geological map of Europe. Okay, so you recognize here the Ural Mountain, the Scandinavian Shield, the North Sea, the Mediterranean Sea. So that's the geological map of Europe, the one that was published by the Big Air. Okay, and the other one is the DEM of Europe, sea, land one. So, and the question that I ask you is, what's the way using those two documents to say this zone is an erosional one, this one is a depositional one? I ask you the question. So if you have ideas, ideas welcome. And again, this is very, very simple, very basic. And we will do that for the, I did a zoom. So this is Western Europe, and the same for geological map and DEM. Do you know about that? Are there somebody that want to answer the question? So to access to the, for me, it's not easy to access to the, what's the way for me to access to the chat? I cannot access when I share my screen. So are there somebody?
The relief can be an indicator.
Je pense que tu peux, François, tu as une petite barre que tu vois verte?
Yeah.
Bah, si tu vas dessus, normalement, ça t'ouvre un menu.
Yeah, but quand je clique dessus, ça ne fait rien. Ah si, ça y est.
Voilà, et là, tu as mort. Tu dois avoir mort, par exemple, ou plus, des options, et il y a conversation peut-être. Tu vois pas ça?
No, the best is that we are not so much, so you can talk. So that's the easiest way. Okay, well, what you said.
Maybe the relief can be an indicator.
Yeah, the relief could be an indicator. Okay, and what specifically in the relief?
I guess the smoothness and how flat it is as well. How smooth.
If it is flat.
And the smooth as well. If there's not, it's not very desiccated, not very rugged.
Yeah, desiccated. That's good. That's a good point. So if it is desiccated, it's because what? What's the cause of desiccation of relief?
Yeah, it suggests more erosion than deposition, right?
Okay.
Yeah, there could be rivers cutting in.
Yeah, rivers cutting in. Okay. So this is the point. If you get an erosional relief, you have to have the processes shaping the relief. In the case of Europe today, this is the rivers. You have to have the rivers cutting through the relief and to get what we call incised valleys. Okay, so this is the first order. So if we check what's going on in Europe, so if I take the Rhine, you know that the Rhine is cutting through the Rhenish Massif over there. If I take a famous river here in the French Massif Central, the Aveyron is cutting through the coast plateau. So if I look all around, even the Seine, okay, so if you look here on the DEM, you clearly see that the rivers, all the rivers in Europe are now eroding the landforms. And the best proof for that is that you can do a geological map. If you can do a geological map, it's because the rock is cropping out. If the rock is cropping out, this is not depositional. You agree with that?
Yes.
This is really basic. And on the other hand, how to identify a subsiding depositional area? It has to be a surface covered by recent quaternary sediments. You agree with that?
Yes.
Okay. So if we look at the legend of the captions of the geological map of France, of Europe, sorry, there are two points that are interesting. They are Q and N2. Q is the place where you get thick quaternary deposit, okay, and N2 is where you get Pliocene plus thin quaternary deposits, okay. So it means that the places, so if you look, where are the places where you can expect subsidence? It's the North Sea and the Netherlands. Okay. This is here the Po plain. Okay. This is all the Mediterranean margins. This is maybe the Rhine-Graben. But for the rest, nothing is subsiding. Is that okay for everyone? A subsiding domain has to be a place made of quaternary deposits, okay? This is basic. So if you get deposition, the geological map has to indicate that you are looking at quaternary deposits, okay? Over a large area, because you know that the INCISED Valley, you can get terraces. I will be back on that. So, and this will be indicated as quaternary, but this is a little strip, okay? So it has nothing to see. So it means that the places that can be subsiding is Netherlands and North Sea, Po plain, the Mediterranean margins, here in Galicia and in Portugal, the margin, and that's it for the rest. The conclusion is that it's uplifting, or this is zone in transfer. Is that okay for everyone? You understand the principle?
Mm-hmm. I've
Okay.
got one question. In the Mediterranean, there's this bluish color. Is this just the sea? The seawater?
In the bluish, you have, sorry, the bluish, you have two blue, unfortunately. You have this blue, and you don't see because the resolution is bad, you know, and it's a little bit, and there are some whiter dots. Do you see them? Okay.
No. Okay.
You don't see. It's where is my arrow. Okay. Mm-hmm. You see my arrow. Okay.
Yeah.
This is a place, and this one as well. This is oceanic lithosphere. Okay.
Okay.
And recent one. That's why it has the color. And the place that is in sedimentation, it's here the Gulf of Lion. Okay. Here, this is the Tyrrhenian Sea. Okay. This is here on both sides of the Balearic Island, Mallorca and Minorca. So this is the places, or here in Galicia and Portugal. And here, there are also an evidence. In that case, this is exhumed mantle, so it's not easy to identify. But this is the place where you get quaternary. The Adriatic Sea is something subsiding as well. Is that okay for everyone? You understand the principle? So if you look at the, sorry. So if you back to the topography, the topography, so it makes sense. So if you look at the southern North Sea, the Netherlands, so you know this is a very flat area, so that makes sense for a depositional system. Okay. And if you look the Po plain, yeah, if you look, this is a very flat area, so that makes sense for a depositional system. You understand the way to use DEM and geological map at the first order to say this is subsiding, this is not subsiding, okay? If it is subsiding, it has to be, you buy a geological map of gray to blue color. It has to be all the time quaternary deposits cropping out, okay? And if it is an erosional one, you have to have erosional landforms. And in Europe, the erosional landforms are INCISED Valley. And if you look all the main rivers, I took the Rhine, I can take the Meuse, I can take the Seine, I can take all the major rivers, the Ebro, I can take all the major rivers in Europe. If you look at them, most of them, if not all of them, except the Rhine, in the last part of its profile, everything is in erosion, and the result is that you get erosion. Is that fine? And in the future, when we will be able again to travel, this is a question that you have to ask you all the time. For example, imagine that you go to Argentina for holidays or for any reason, look around and all the time try to say, is that a depositional? Is that a transfer? Is that an erosional system? Just look at the landscape, look at the map. Okay, so that's really an exercise that all of you have to do. And they are Brazilian people, they are Indonesian people, they are Venezuelan people. Brazil is a marvelous country to identify places where you get deposition, when you get transfer, when you get erosion. And please look at the DEM and a geological map of Brazil. And next time we have to meet us, you have to tell me where are the subsiding places in Brazil, where are the uplifting places in Brazil, and where are the active places of uplift in Brazil. And so this is really something very important. This is an exercise, the same for the Indonesian people as well. So please do it. Please do it. And all the time ask you the question, what's the status of the landscape where I am or where I live? So that's very important. Okay, so for Europe, there are few places in deposition for continental Europe, here, and a little bit in southern France, in Camargue area, and that's it. For the rest, it is uplifting and eroding. And the cause of this uplift is, of course, the convergence between Africa, Apulia, and Eurasia, okay? So that's, if you look at the first order, you can describe Europe as a tilted plateau, okay, except for UK. Is that clear? I would like to have a discussion with the Brazilian people. Check. I love your country for geology. That's marvelous.
Yeah.
Okay.
Not that many, I guess, depositional areas, but the ones that there are really interesting, as you said.
Okay. So now I have to be back to more classical knowledges. So please again, if you know, that's fine. If you don't know, it's something that you have to know. So the main question with the erosion is that we have two kinds of erosion, a physical one or a mechanical one. And another one that is chemical erosion. And today, the key question is the balance between chemical and physical erosion. And you clearly understand that the product of erosion are very important for the chemical budget of the Earth, and mainly the chemical budget of the ocean. This is something that is very important. And this balance, what are the role of the climate and what are the role of the tectonic in that balance, okay? And I will tell you in a couple of minutes that unfortunately we know very few about chemical erosion, and it's why some of you are working on those kind of questions, because honestly, it's something that is highly debated. Okay, physical erosion. So this slide is quite boring. For the one who got a classical geological surface processes culture, it's something that you know quite well. So just I repeat that the effect of ice in terms of erosion, it is what we call abrasion scouring, plucking or quarrying, and ice rusting. So what it means, so it means that you know that if you've been in in glacial landscape, you see surfaces with striation. So this is abrasion and scouring. You can see places where you get blocks eroded. This is what we call plucking and quarrying, and ice thrusting, you don't care. But by the hand, the result is to get as the first deposits over those erosional surface, what we call tillites. Okay, and everybody has to know what a tillites is. A tillites is the first glacial deposition over those ice surfaces. So this is a conglomerate dominated by fine-grained matrix in which you have striated blocks. So if you don't know about that, it's something that you have to know by yourself. It has to be part of your culture. The second process is wind. And I will spend more time about wind because you understood that wind is able to transport particles and to modify the source-to-sink budget. So this is important. So you have two ways to do that, or you remove loose rocks, whatever the loose rocks, okay? And all the fine to medium grain particles, so it means less than 1 millimeter, can be transported by winds over thousands of kilometers during one storm. So it means that it can be a quite long and efficient transportation, and you can modify the budget, is what I showed you this morning with the Sahara. The other one is what we call, again, abrasion. So this is a kind of sandblasting effect. So it means that if you've been one time in a storm, you get a wind with a lot of little particles. And if you have no clothes, it's real trouble with your skins, okay, because you get cleaned by the sandblasting effect of all the system. And this is really the way to wearing down hard rock and to get new particle in the sediment budget. Okay, so this is really the process, and I will show you in a couple of slides about that in a couple of minutes, because that's an important point. Jean and Seb will talk a lot about water, so I will be quite brief on water. Of course, you have surface runoff that transport loose sediments that you remove during rainfall by gravity. There are different effects that probably you heard about: splash, sheet, real gully erosion. And you have the stream erosion, and this is a point that you have to discuss a lot, so I don't want to focus on. And the last main process is mass movement, okay? Due to gravity, this is rock falls, landslide, mud flows, and then so on. And there are a last process that is not considered as an important one, but maybe it's wrong. It's rock cracking by contrasting temperature changes. It could be a daily one or a yearly one. For example, I don't know if you got the chance to be in the desert. So in the desert, it's quite cold in the night. I've been many times in the Sahara, and during the night you can reach 0 and sometimes -4, -5. And during the day you can reach 40 degrees. And the effect of this daily change of temperature implies that in the morning, so the desert is a marvelous place, so you get an absolute silence. There are no insects, nothing. Just what you hear in the morning when the sun is rising is the rock cracking. Okay, so this is really a process that you can understand, and that's quite efficient in in some eolian. Another way is, for example, in that case, a yearly process. So probably you know that in Siberia or in northern Canada, everything is frozen. Okay, all the top of the rock is frozen, and it's frozen during I would say 9 months, and sharply in May or June, in a couple of days, everything melts. Okay, and the freeze will be as fast in September. Okay, and then at that time, you because of the melting of the ice, okay, you get an expansion of the water because of the freeze process, and because you melt, the rock is cracking. This is the same type of process that what you have in the desert. So it's a very efficient process to generate pebbles. Okay, so please keep that in mind, and then we show you some example. So I think that most of you already known about that. So and that this is nothing new, and I will just insist on the wind system. So ice, that's beautiful. You will get yes, water and mass movement. Jean and Sebastian will be back on that, and I insist also on that. So just to show you what a deflation surface in the Sahara, it's what we call a REG, R-E-G, and what's the way you get a deflation surface is that you get a loose rock. Most of the time, this is an older sediments, and most of the time, this is a former fluvial sediments at time or during the interglacial period where the desert was humid. Okay, so it means that the desert changed to a large alluvial system. So, and you get river and that are able to mix the sand and pebbles. Okay, and when you dried again this area, what's going on is that the wind is active, and the wind is progressively removing all the fine-grained sediments less than 1 millimeter, okay? And you get a concentration and polishing of the rock, okay? So it's what you observe. And you have to imagine in terms of volume and then in terms of sediment budget, and it's why you insist, is that at the end of this wind activity, that could be about 1,000, 10,000 of years, all the sand is removed, okay, transported far away over hundreds of kilometers, and what is left is just a pebble, okay? So it's quite important in terms of sediment budget, and I will insist on that later. So just an example of those surfaces. So this is in Namibia, in the Sperrgebiet. So if you look, so this is a zone made only of pebble, okay? So this is pebble, okay? And you have just coarse-grained sands on top, all the medium to fine-grained sands, and this removed toward the large sand seas, or toward the sea, depends. And this is what we call a deflation surface. Okay, and at the beginning, you have to imagine that it was a fluvial system, and only what is left is the coarse grain particles. All the fine grain were removed by the sand. So just for fun, because this is the rock that I really love, so the wind is able to polish any kind of pebble. So you have this sketch explain the way you get this polishing. So below you have the round shape of the pebble, and because of the sun-blasting effect of the wind, you progressively cut through the rock and polish it, and you get what is characteristic of aeolian deposits that we call ventifact and tricanters. And when you find them in the middle of a tropical forest, it means that the tropical forest was dry and hot at a given moment. So that is a very good indicator of hot, arid climate when you find them. And I mentioned this morning this Triassic period where you reach an estimation of 28 degrees for the Earth. And one of the arguments is to find everywhere on the Earth that kind of pebble. So this is one of the used arguments for that. So chemical erosion. So it means that mostly we understand the physical processes. There are no discussion on the process. It's something okay. So chemical erosion, this is not the same question. Okay. So probably you saw this map. It's in a lot of textbook. This one is published in the famous Allen and Allen book, the Allen's brothers book, published in Blackwell, now Wiley. This was the second edition. If I understand, the third one. And this picture is coming from the Russian and Soviet school that was very efficient in the 50s and 60s. And the objective of the Soviet school was to do global understanding of the Earth. For example, all the discussion on the sediment budget, the paper of Molnar in England, is based on the word measurement of the siliciclastic sediment volume, and this is based on those Russian work. So it means that the source of the discussion of the Molnar England paper is based on the data compiled by the Russian Soviet geologists in the 50s, 60s. So it means that this is also something that we have to question to make sure how true is that or not. And what is, if you look at this map, you see zone where you predict intense weathering. That's fine. This is in that brown orange. Okay, you have zone of moderate weathering. This is the zone where you get this brown pink one. And you have a zone of low temperature and low chemical weathering is what is all what is to the north. Okay, so that's it. Okay. And if you look at the balance published by Sommerfeld and Elton, okay, if you look at the balance, what you, Cécile, you can stop your microphone. Cécile, you stop your microphone. Cécile, you stop your microphone.
Sorry.
Okay, and so if you look at the balance and the amount of solute production of all those rivers, and if you look at the ratio between the mechanical and chemical, you see that the Ob, Siberian River, the Yenisei, Siberian River, the Lena, Siberian River, and the St. Lawrence, that is located on the shelf, are the places where the ratio between mechanical and chemical is the highest, and the amount is not, of course, the one of the large rivers, but it's not nothing. Okay, so it means that this is wrong. This model that is very popular is wrong. We have a lot of chemical erosion in that area, in this area as well. And there are some people working on that, and mainly in France, Jérôme Gaillardet in the IPGP. And what they say is that, what is important to get chemical erosion is not to have hot water, it's to have water. Okay, so that's the key point. And at the moment, it means that we don't know the exact distribution of the weathering and what are the products. I will tell you in a couple of minutes that it's quite well understood for the lower latitude, but honestly, in the higher latitude, we don't know exactly what means. There are a lot of work at the moment on those one, but again, do not believe the textbooks. So it means that this famous figure you have to be really careful about. So what is true is that the maximum weathering with laterite and so on is located at low latitude. This is true that the desert are places where you get very low chemical erosion, but to the north, to the high latitude, this sketch is not true. Okay. So just a picture of Nikolai Mikhailovich Strakov. And beyond that, you have to imagine that was in the 60s, that was in the 50s. They did a lot of compilation. That was a lot of work, but again, we have to question that now. Okay. We have to talk about the soil associated with sediment production, and because soil geology is something that is really boring, I would just show you two types of soils that you have to know, that are very typical, very classical, and that are quite high producers of sediments. And this is something that you have to know about. So this is Africa. And you know that all around Africa, there are what we call laterites. You heard about that word. You know that laterite is something used in those countries for building roofs, for building some houses. So this is a hard rock made of iron. It's around 90% of iron and 10% of aluminium. Okay, so this is the composition of the what is called laterite, and this is something that is all around Africa. So what is a laterite? Okay, and this is something key for the relief for the sediment production and so on. So if you look to a laterite, this is a place at the base where you get hard rock, the original rock. Okay, and progressively over that rock, you pass to something that is soft. A soft rock made of clays, okay? And on top, again, you get something hard and very hard that we call the iron dairy crust. So it means that, first of all, the parent rock, that could be a mica schist, that could be a gneiss, that could be a granite, that could be a basalt, that could be a dorite, that could be whatever you want, is first transformed to a soft rock made only of clays that we call kaolinites. The clay that is produced in that profile is what we call kaolinite. And this zone of subsediment that can reach sometimes 100 meters, that's a lot, is what we call the saprolite. Okay. And again, on top, you get, as I already mentioned, you get this very hard zone, the iron dairy crust used by people that is 90% of iron and 10% of aluminium. Could be, in some case, 90% of aluminium and 10% of iron. And in that case, this is what we call a bauxite. This is the origin of bauxite. So at the base is what we call the weathering front. So this is the boundary between the parent hard rock and the transformation, the soft rock. And what's the way the system works? So laterite is what we call a destructive soil. So it means that when you get a growing of the soil, you destroy the parent rock, okay, because this system is moving down, eating, transforming the rock, okay? And you have a double chemical front. The first chemical front is according to the Goldschmidt laws. The first one is to transform, to dissolve the sodium, the calcium, the potassium, all those elements. And what you cannot dissolve at this moment is quartz, okay? And except quartz, all the silicate are transformed in kaolinite. And later on, you get a second front where all the silicate, including quartz, are dissolved, okay? And what is left is what cannot be dissolved. It's the aluminium and the iron. Okay, so you understand the way work this machine, and you imagine that all the rock is, except at this level, is except the aluminium and the iron, is evacuated, is waste in the rivers as solutes, okay? And those solutes will be recombined in the marshes, will be recombined in the sea to get clays, to get carbonates, to get a lot of elements that we were talking about before. Is that okay for everyone? You understand the importance of weathering processes? And this morning, when I was talking about the Eocene climatic optimum, you remember, you have to imagine that all the world except Central Asia, part of Argentina, was at that moment covered by this kind of soils, okay? So, and in Europe, probably you know that, and in Brazil, of course, and in Europe, if you cross Europe, you see zone where you get without rocks, a white clay. You get it in Belgium, in Scandinavia, in Scotland, in France. And this is kaolinite. This is the remnant of those old weathering profile. So how it looks like. So this is a crossroad, cutting road, sorry, in South Africa. So here is the saprolite. So this is a soft rock. You don't need any hammer. So and here is laterally the hard rock. So it means that here you get the transition from hard to soft. Okay, and this is the initial rock. The parent rock here in the case is a conglomerate. Okay, and this was an hard rock. Okay. And now, if you take the matrix of the conglomerate or the pebble of the conglomerate, everything is transformed in kaolinite, okay? So it means that all that is a soft rock, okay? So this is what is the characteristic of a laterite. So a zoom at the transition between the unweathered parent rock and the weathered rock. And here you have a nice example of what is the weathering front, okay? So the weathering front is the zone that is the boundary between weathered and not weathered. And what is very key for the rest of the talk is that this zone is not a flat surface. It might be a flat surface, but this is something that has a topography, and this will control the relief later on. So you understood, I did not put that, is that the laterite is the provider of a clay. There are three main types of clay. I will talk about that, not this time, but another time. This is aelite, smectite, and kaolinite. And this is important in the source-to-sink system. And the way to form kaolinite is laterite. There are another way by hydrothermalism, but the supergene way to do kaolinite is laterite. If so, it's hydrothermal in origin. That's fine. So another type of soil, if you've been in Morocco, if you've been in Tunisia, even in southern Spain, or in some part of Greece, this is what we call calcareous soil, a generic name. It's what we call calcretes. And what is interesting is that those calcretes are superimposed over a parent rock. Yeah, in dark is the parent rock, okay? And this soil is not destructive. So it means that it's just something that is on the soil. There are no real ability to weather the rock. It's just something that contributes by the way the calcrete destroy the rock is just by cracking. So if you look, you see that this rock is full of fractures, and the way the soil erode the system is just because there are carbonate precipitation in the fractures, and because just of the growth of the veins of carbonate, you crack the rock. So this is the only way to get an erosion. So when you are in front of calcrete, it looks like nothing. It's not very exciting as a rock. It's very common, okay? So again, there are plenty in Spain, plenty in Greece, in Europe, okay? So how it looks like, it's not very beautiful. Okay, just to show you some detail. But what is important is, again, this is an incredibly fantastic machine in terms of clay protection, okay? Because this is the place where you will generate smectite, another type of clay. And we will discuss probably when we'll be on the field all the social, societal, industrial implication of what we do. And keep in mind that the understanding of the sills, it means places where you can store any kind of waste is something that we have to understand, okay? And I forgot to say that, calcrete are characteristic of arid zone with one humid season. So it means that it is arid, but during a couple of days, you have a quite intense rainfall, but most of the time this is arid. So this is characteristic of hot temperate system or to subtropical system. So this is the calcrete, okay? So I hope we will see some fossil one in Spain, so I can be able to show you that. Second part of this course is, and last one, is after discussing the processes, we have to discuss about the erosional landforms. Okay. So this morning, even I know that Seb is not necessarily, do not necessarily agree with that. I shown this slide, and I shown you the difference between orogenic and non-orogenic relief. It's a beautiful example. So we did some focus on the front of the Himalaya, and even at that scale, you clearly see that the characteristic of the Himalaya is that to be full of incised valley. Okay, so this is really what will be characteristic of orogenic topography. Okay, and on the other hand, if we compare with an anorogenic one, okay, you see that a very different system. They are plateaus. The Eastern Ghats, here some plateaus, the Sapota range or more lowest elevation one. And there are some incised valley as well. So here you have a good example, but it's not as dominant than in the orogenic system. So they are not really no position between what is orogenic incised valley and anorogenic. So you get incised valley in both cases, but what is really characteristic in anorogenic system is those large plateaus and related to planation surfaces that I have to discuss with you soon. So first of all, incised valley. So I really like this old sketch of G.R.L. Allen, one of the fathers of the sedimentology, sedimentary structure analysis, understanding of the physical processes. And G.R.L. really insisted on the fact, and we forgot about that, unfortunately, is that you can get depositional system, you can get erosional system, and in the erosional system, we can get some with a period of deposition and some with no deposition at all. Okay, and this is really what we have to think about. And one point that we have to think is that the slope of those different systems, and this morning the Himalaya is a good example. For example, we get braided rivers even in erosional steep slope and in lower slope. So, and it's known for a long time that you cannot relate fluvial system to only the slope, that other parameters has to be taken into account. And this one is something that we have to think about. But this is a point that maybe we have to discuss during the next week. But when you look at a fluvial system, really you have to say this is depositional, this is bypassing, this is erosional with or no preservation. It's really something that you have to think about. And I'm not sure, this is a point that we have to discuss, that you can use data coming from a pure erosional one to something that is depositional. This is a point that we discussed with Seb, and I think that on the field we can discuss again on this point. Okay, good example of an incised valley. So here, braided system, this is incised valley, you have lateral system, everything is erosional. No doubt about the status of the landscape. So, Seb told you about the progress in geomorphology during the 20-30 last years. So of course we are far beyond the description of the system, and we know that the dynamic of the valley erosion is a combination between the talweg and stream dynamic. So it means the erosion by the river itself, plus hill slope processes. And hill slope processes, what are there? They are mainly mass movement, okay, and mainly slumping, sliding, and runoff. And it's really a point that Jean will show in modeling approaches. So it's something that is now very well understood in terms of physical geomorphology. I just want to focus a little bit on terraces. So terraces is something that is used a lot by geomorphologists and geologists. And may I say that beyond the word terraces, there are really different processes in the back. They have not a single origin, they are different processes, and mainly depending on the climate. Okay. So a very nice example of terraces here in Central Asia. So what is a terrace? Okay, so here's the river. You get the first zone of rupture, first banquet, okay, over there. Then you get another one and another one. So it means that what you have here, this is a terrace, this is a terrace, this is a terrace. In the back, you get another nice evidence of terrace over there. So this is what we call fluvial terraces, okay. And another example in New Zealand, okay, you have the river in the middle, and here you get terraces, what we call an unpaired terrace. They are not equivalent of the other one, but this one, if you look on, this is the same level, so this is what we call a pair terrace, because you have two twin ones. So this is what we call terraces, okay? And the way that terraces are related, so there are different types of terraces. You have what we call cut and fill, you have strass terraces. There are plenty of terraces, so I don't want to be in the detail of the different type of terraces, and I took a very simple one. So it means that you have a terrace, and each time associated with the terrace, you have sediment deposition. Okay, it's what we call stepped terraces, okay, and it's what is generically related to cut and fill system. So the way you form this one, so to get incision, you agree that you have to have uplift. That's fine for everybody. To get rivers, incising, you have to have a uplift of the system, but superimposed on the uplift, you have to get this discontinuous record of the incisions, climate variations, okay? And the classical model is this one, sorry, is that you start with a flat surface, you get at T1A, you get incision, at T1B, you get fluvial aggradation, at T2A, you get incision again, at T2B, you get aggradation, and then so on, okay? This suggests a discontinuous process, but probably it's not. So it means that the uplift is something that might be continuous, sometimes increasing, but this is not a discontinuous uplift. Each terraces does not mean uplift, stop, uplift, stop, uplift, stop. It's a continuous process, but the climate induce discontinuities. And again, here is the climate fluctuation. I cannot put on this curve, that could be hot humid, for example, where is TA1A, TA1B, it depends of the type of fluvial system that we are looking for. It depends of the climate, it depends of a lot of things. And there are several possibilities of relationship between climate and terraces formation. So this is really a point that I insist on. So of course, the classical model is the one associated in the mountains with a glacial input. So of course, most of the glacial input is at time of the glacier melting. Okay, but this is not the truth for all the terraces in the world. Okay. So again, some European example. I will take a European example. So this is I shown the Rhine system, okay, with the different possibilities of evolution at time of low stand toward the North Sea or toward the Atlantic. So this is the Seine and the same. So this is the point discussed when it is this way or this way. And here is the Meuse River, okay, and just to show you a nice example of terraces dating. So this is a compilation of by Bridgeland of a lot of Dutch and Belgium authors. So here is the mapping of all the terraces of the Meuse River around Maastricht. So if you look, you have all those terraces, okay? It's quite asymmetrical, and this is based on different techniques that I will talk about. It's possible to get ages, 10 million years from this one, 3.1. And here you have numbers, okay? And those numbers corresponds to the isotopic stage of the Pleistocene. And for example, where is isotopic stage M22, it corresponds at 1 million years. So it means that here, this is younger than, it's between 0 and 1, and this is between 1 and 2.8, okay? So it means that at the beginning, the incision of the Meuse is quite slow, you agree? Between 10 and 6, 6 to 31, 31, 22. It's getting a little bit faster and faster again for the most recent period. Is that okay for everyone? You understand the way it works to use terraces and to date them, to have an idea of the uplift, and looking at the sediment infilling of the terraces to have an idea of what are the processes of deposition and how they relate to the climate. Okay, so again here the Meuse incision is a continuous process. There are no discontinuity. It's known. It's related to the Eiffel plume that is at the origin of the volcanism in that area. So this is the dynamics of, it's one of the best documented one in Europe. Okay, just an example of some infillings from very coarse grain one. This is in Morocco. So you have the basement. This is the infilling of a terrace. This is in France. This is in Middle Loire, close from Tours. Okay. And you see it's made of coarse grain sand with a lot of current megaripple deposits, okay? And so this is for the Loire and for the Somme, okay? And if I look to the Somme river, so if we look to the Somme river, it's something that is completely different. What you have here is fluvial deposits, and all those fine-grained sediments that you have here, here, and here corresponds to what we call loess. That is an eolian sediments. So it means that even in terraces, you can get eolian deposits, okay? So I'm back to what I said to you this morning, and this is applied to Europe in that case, Northern Europe. Okay, so during interglacial period, the climate in Europe, France, Belgium, Luxembourg, Germany, is cold temperate. Okay, and in between, the climate in those areas corresponds to a peri-glacial climate. Okay, so it means that this is the type of climate that we have now in Siberia, northern Siberia. So you have to imagine Siberia in Europe. And what you get in Europe is a huge permafrost. So it means that the rock and the soil are frozen on a thickness of 100 to up to 800 meters for the maximum. So that's a lot. You have to imagine everything. You have to imagine everything frozen, okay? So it's very well dated, and the process is quite well known. So again, it's what I said this morning. So it means that during the period where the soil is glaciated, few things occur. What is critical is the period where you melt the permafrost. You imagine that all the water of the permafrost are transferred to the river. Okay. You imagine that all the rocks that has been frozen, defrozen, frozen, defrozen are fractures, and you get plenty of pebbles, on top of the rock, okay? And in less than 100 years, I will show you that in a couple of minutes, you get a high increase of water because of the permafrost melting, and you have on top of the permafrost plenty of pebbles available. You imagine the rivers. The rivers have plenty of water. They're able to transport sediments. They are, of course, grain sediments. And all the quiet rivers that we have in Europe, could be the Somme, could be the Seine, could be the Meuse, could be whatever you want. All the rivers become a kind of furious river during a couple of years, okay? So everything is well dated, okay? And so just to show you how sharp is the climate change. So look, we are at 15,000 years. This is the end of the first glacial period. And in less than 100 years, everything is melted. That could be the glacier, that could be the permafrost. And the consequence is the incision. You decrease again the temperature. You get a second phase of freezing, okay? You get again defreezing, and then a second incision and deposition. So it means that what is important in that case, and it will be different if you are in Indonesia, if you are in Brazil, if you are in Congo. This is true for a given climatic belt, okay? So, and this is true for Northern Europe, okay? So in Northern Europe, the way work the incisions and the terrace aggradation, it's when you increase the amount of water and of sediments due to the melting of the permafrost. And this is something very sharp, very brief, okay? And in between, few things happen. Okay, last point for the terraces, just to show you the way you can use them to quantify deformation. And this is a work that I really like. It's again a compilation of work of different German authors and Dutch authors as well. So this is the Rhine. This is the Rhine. so here is the Rhine. So you go from here, Mayence, Wiesbaden area, so just at the end of the Rhine-Graben, you cross the Rhenish Massif, and you arrive in the Ruhr basin, subsiding basin. Okay, this is the Ruhr. This is Wiesbaden, Bingen. Okay, Cologne, Köln, Bonn. Okay, so you have all the cities along the Rhine. And here you see what is depositional, what is erosional. Okay, so you agree that with the terraces, this is exactly the opposite of what we have in the deposition. So it means that the oldest terrace is on top. You agree? The oldest is here. Okay. In the sediment, the oldest is at the base. Okay. And at the moment, here, if you look, HT2, you move from a place that is in deposition, okay, to here. That is the place that is in uplift. So it means that here you can clearly map the point that corresponds to the transition of depositional to erosional system, subsiding to uplifting domain. And the hinge point between subsidence and erosion, uplift, is located over there. And if you look over time, it's migrating. Okay? And if you look at the mapping of the profile of the river, of the terraces along the river, what is great is that at the beginning, if you look, you get the same amount of uplift here and here. So it means that you get an homogeneous uplift. You agree? And when you change at 62, or 68, sorry, here, if you look, you change the mode of deformation for a regional uplift of all this domain. You go from a place that is an hinge line with an uplifting zone upstream and a subsiding zone downstream. So it means that you change the deformation regime, okay? From 82 to 68, you get an homogeneous uplift of all this area. And from 68 to today, we get a differential uplift. And you can prove that this is really uplift because you get a geometrical feature that indicate a differential of vertical displacement in space that is an argument for tectonic and not for climatic origin, okay? And it's why I disagree with some of the conclusion of the Molnar and England paper, is that this is known by the German geologists since, I would say, the 70s and maybe earlier. And when the German people say, we have a recent uplift of the Rhenish Massif, this is based on data. This is clearly tectonic. This is not climatic. Okay? And based on the mapping, on the 3D geometry of terraces, you can have an idea of the recent deformation of a given area. And here in Germany, this is known, I would say, in the middle 70s, there's a famous paper of Fuchs describing the kinematic of the uplift of the Rhenish Massif and the Ardennes. It's something that was known. So honestly, so this is a very powerful tool. The main problem is really to date the terraces. And we will see that this is not something very easy. So last point for the INCISED system, the terraces. So at the moment, yeah, this is incredible, the techniques that we have, the number of lab that work on terraces dating. So it means that we have really the techniques, the technology for dating terraces, even it's very expensive. Sometimes it's very, how to say that, it's not very easy, but all the time you have to be able to relate to geology. So if you do dating, not understanding what you date, you're sure to succeed. So this is really the point that I want to insist on. And if you have to work on fluvial terraces, if you have sediments, you have to be sedimentologist. Just to give you an example, the first dating of some terraces did not understand that most of the sediment were eolian in age, eolian due to eolian processes. And they say crazy things because they considered that they were fluvial system. But if you know that this is eolian, this is a very different dynamic, and you do a different interpretation. So it means, again, you have to be geologist, okay, and to integrate everything. And the first thing working on terraces is to look at the sediment. Okay, so we have classical radiocarbon C14 techniques, so you know the limit. You cannot go far than 40,000 years. You have marvelous new technique, OSL, electron spin resonant on quartz, ESR. Those techniques are very powerful, but really it's a lot of work in the lab. The analysis of the sample takes a lot of time, so that's you have to know what you want to do doing that kind of technique. So it means that you cannot go on the field, take a bag of sand and be back to the lab and say date that. No, you have to have a strategy of dating. I'm not specialist of this kind of things, but I have many friends doing that kind of work. So honestly, this is not easy to do. You have first to understand what you want to date before to date it, and to define a strategy of dating. Marvelous techniques. Yeah, the way you can now, if you have ENIAF uranium dating to C-noble, so that's very nice technique, and the same for carbonates, very powerful. And you get classical cosmogenic approaches, or surface exposure dating or burial dating. I'm not very familiar with that. So I really do not appreciate this sketch. It's too complex, but I did not find better. So if you look, you can date the sediment. You can have an idea of the inheritance. You can date a surface with no sediment. You can date a surface with sediments. You can get the hill slope, okay, using a cosmogenic, and the storage and by burial dating. There are also marvelous technique, and I saw them apply in the Pyrenees when you get carbonate rock in the catchment on the old slope. So you have karsts, and what is interesting is that the karst adapt to the successive level of the river. So it means that when the river was there, you get a karst connected at this new level, and then so on. And then step by step, you get fossil fluvial deposit in those karst, and you can date them using different techniques. So this is a very, very powerful technique. And for example, in the Pyrenees, we were able to prove that the uplift of the eastern part Pyrenees were starting 20 million years ago in the eastern Pyrenees. So that's very nice, powerful techniques. So the main limit, and this is a question that I would like to ask you, is that terraces in the geological record, there are not so many. And this is a point that intrigued me, though there are plenty of terraces between 1 and 0 million years. There are some between 5 and 3. As I showed, there are very little between 15 and 5, and I don't know any terraces before, so the explanation might be simple. Is to get terraces, you understood that you have to have a sharp, high amplitude climatic variation. We know that this is eccentricity cycle between 1 and 0. Between, it's not between 5 and 3, it's between 5 and 1, sorry. Between 5 and 1, we know that there are some climatic controls, okay, here also, but before. So, and the question is that possible to get terraces preserved in the geological record before glacially forced climate changes? So this is something that I don't know, but I'm sure, yeah, this is a point, an important point, okay? Okay, so now and briefly, because you're getting time, me too, and I would just talk about anorogenic relief and plateaus and planation surfaces. So this is something that we have to discuss when we will be in Africa, so I will be a little bit fast on that. So if you've been in Africa, but for the Brazilian people, it's something that you know, if you've been on top of Minas Gerais or in some places or in Paraguay, those anorogenic are characterized by very flat surfaces. So this is the Bushmanland pediplain. This is in South Africa, at the border with Namibia. So you say, well, yeah, that's a plain. That's a plain, okay, that's a plain. But the main problem is that this plain is at an elevation of 1,500 meters, okay? That you just have 10 or 20 centimeters of sediments, and what is below, and you have some example here, is the rock, the hard rock. So it means that this surface cuts through different lithology, and in the case of South Africa, it's Archean to a Neoproterozoic rock due to various orogenies. So you get those incredibly flat surfaces along great distances, and this is one of the characteristics of those anorogenic systems. Been in the Deccan, Eastern Ghats, you get exactly the same kind of things. Okay. Just now looking at the DEM, we are in Nigeria. There are rifts over there that we call the Benue, and if you look at this DEM, you see those flat surface. So if you look here, even you get a quite strong vertical exaggeration. You see a flat surfaces. So again, there are no sediments. So this is a pure erosional one. You get another one downstairs, another one downstairs, not at the same level. This one is at the same level, another one downstairs. And this is what we call pediplain or pediment, okay? So this is a flat surface that passed to the one above with an escarpment in between. Okay, so you clearly see this nice escarpment. So you get here an erosional surface with a scarped stream. This is what we call a pediment. You get another one here. You get another one here with a quite steep pediment. So it means that the dynamic of the erosion, the dynamic of the landscape is those kind of settings, and is really very different than what you have related with the incised valley, but we will see that this is not the same processes, that this is not the same duration in terms of processes. To get that kind of landscape, it takes millions of years to get them in very specific climatic setting. So we have them in the French Massif Central, in the Rhénish Massif, in the Ardennes. So it means that those reliefs exist, but they are incised by younger rivers. So just to summarize what we call a pediment or a pediplain. So it means this is a flat surface, okay? This flat surface is purely erosional. You have no sediments. What you have below is the rock. So it could be a granite, mica-schist, gneiss. Don't care, they cut through. And you get a scarp upstream. Sometimes they can be controlled by a lithological change. Quartzites is terrible for that. You can get very steep scarp, less or more progressive evolution from one to another one. And this is a sketch of what it is. So this flat surface is common, and upstream you can get some incised valley connected to that system. So just again to show you some example, so this is in South Africa. We're not very far from Cape Town. This is the Cederberg Massif. So if you look again, this is not subsiding area. This is pure planation surfaces, okay? Below you have rock. Here, this is the famous Karoo sediments, famous for people working on tubiditic sedimentation that are cropping out. And if you look, you get several pediments and flat surfaces. And if you look, there are really few incised valley. There are some. If you look here, you get a nice incised valley, a nice incised valley. But those ones are younger than those surfaces. Okay, so there are some ideas about the time you need to have a pediment. So we are talking about million years. The rate of downwearing. So it means the deepening of the flat surface or the backwearing, the retreat of the escarpment is quite low, okay? And we did an estimation for the African one, so we talk about million years. So we will see what kind of process might be involved to explain that kind of system. So what is interesting is that we know that those reliefs are very old. And this is something that we have to visit if we can be able to be in South Africa, is that we have what we call kimberlites that are explosive volcanism, and on top we have lake. And those lakes are preserved in South Africa. They cross-cut through those very large planation surfaces, and you have ages of the kimberlite. So it means that this flat surface that I showed you in the Bushmanland is a very old surface, because all the lacustrine system related to the explosive kimberlite were not eroded. So it means that this is a very, very old feature. And if we look at the present denudation rate based on cosmogenic in South Africa, the rates are very low, okay? The rates are very low, so it means that most of the African landscape are fossil landscape, okay? And that they were formed under different climatic regime, so this is something important. So that's old relief with not active at the moment. Okay, So just we changed. We're not in South Africa. We are in Uganda. We're not very far from the Rift Valley. The Rift Valley is in this direction. So this is typical of the relief that we can get in Africa. So you get this kind of hilly topography, okay? Hilly topography. So this is hard rock, okay? And all around this hard rock, you get some remnant of kaolinites, okay? So the top of this surface, you know, the top of this relief is flat. You agree with that? Just looking at the relief. And on top of that, what we have is iron crust. So it means that what we are looking in front of us is a weathering profile, a laterite, okay? And just to remember how it's made a laterite, you have the iron crust, the clay, and the weathering profile at the base that, as I mentioned, is not regular. And then what you are looking here is the top of the weathering profile, the weathering profile that has been removed, and the topography that you have is the limit between the hard rock and the soft rock. There are some remnants over there, okay? So in Brazil, this kind of observation, you can do it many, many times. Okay, so this is hard rock, weathered rock, and what has been eroded by uplift is the weathering profile, okay? And the way to form this system is to get first a weathering profile, to have an uplift here, it's probably related to the rift. You remove the weathering profile, and sometimes you help it to get deeper, so it depends, okay? And you get a critical period where everything is removed, just to show you a sketch to explain you the way you form those kind of reliefs. So you start with a weathering profile. This is the dairy crust on top. This is the saprolite, okay? So you get growing of the system, and you uplift this domain and you strip the weathering profile, and what you get at the base is the base of the weathering profile with all these irregular structures that we call inselbergs, okay? And this is the way you get flat surface in between, escarpment, and so on, to explain you the system. So it means that to get those kind of landform, what we call pediment, we have to have hot, very humid period to get intense weathering of laterite type, and then later you have to have very long wavelengths, slow deformation, and most of the time this is something related to mantle dynamic. This is a point that we have not to discuss today, but erosion never stopped. So this is something that is important to keep in mind. So it means that even you change the climate, if you go from a hot humid to hot arid, you still have wind and you still have aeolian erosion. So it means that those structures that were remnant of weathering were later on with very low rate, around 1 meter per million years. You keep the erosion and you decrease or you increase the shape of those rounded system that we call inselberg. Just to show you a couple of examples. So this is in Namibia. So this is not sediments, this is an erosional surface. And here you get a remnant of a base weathering profile, okay? Here it's much more spectacular. This is the Spitzkoppe. And the story is much more complex, okay? Because you need a a lot of weathering, a lot of uplift, and this is something with not only one stage of weathering, but several stages of weathering, something that has been well studied by the Jean's group in another relief not very far from here, okay? And you get those marvelous landscape that we call Inselbergs. So those were related to weathering front, and later on, but at very slow rate, reworked by the Aeolian erosion, okay? So this is the way that I formed the system. And of course, most of the relief in the earth, you can go to in Africa, in Brazil, in Australia, in Europe, are related to this maximum of humidity that corresponds to what we call the early Eocene climatic optimum that I was talking about this morning. Okay, just to show you, and this is my last slide, this is the technique of dating weathering. Again, this is something very important. I'll just show you a result of the dating in Burkina Faso. I will explain you the technique in a couple of minutes. So if you look the peak of weathering, so this is interesting, you get a peak between 45 and 50. This is the early Eocene climatic optimum. You get another one between 24 and 29, and several other ones. Okay, so it means that what the cause of this weathering and the cause of these landforms is something due to the occurrence of those huge weathering period. Okay, so it's very important to date them. So there are several techniques. The one that I really like is the dating of manganese oxides associated with the saprolite, and the one that are very nice is cryptomelan and jarosite. And the way to date them is a classical Hagen-Hagen technique. This is based on Hagen-Hagen technique on full laterite profile. So it means that this is based on 200 datings. Okay, so that's a lot. So it means that we know what's going on. Magnetostratigraphy. So that's something crazy, but it works. It was successful in for dating, for example, the weathering in Scotland. So you do magnetostratigraphy based on the fact that the youngest weathering is at the base of the profile, and the oldest on top, and you can do a kind of magnetostratigraphy on the weathering profile. Now, the technique of dating kaolinite using RPE work quite well. So it's based on the crystallization anomaly of the silicates. So that's a very powerful technique. And the other one is to date high and dairy crust, dating the goethite. And in France, we have a specialist, Cécile Gautron, who developed the technique. And this is an excellent technique. Or the other one is to use paleomagnetism, and surprisingly, it works. So it means that now we were able, and we did that exercise in the Ardennes. We were crossing all the techniques using manganese oxide, goethite, and paleomagnetism, and this is unbelievable how similar are the result that we got dating the weathering profile. Okay, so just to make sure that you understand the way it works, those landforms. Okay, just to make sure. So it means that if you want to get that, you have to have, first of all, a weathering period where you get laterite, okay? And you have to sustain or remove the weathering process by an uplift, okay? And you remove all the all the things, and there are some remnants that you see here or here that corresponds to what we call the Inselberg, and alternation of uplift and climate change. So it means that to get those stepped surfaces, again, it does not mean that the uplift is discontinuous. Could be just a continuous process of uplift. So this is associated with a rift. So probably it's a continuous uplift process, but you have to integrate the fact that the climate is discontinuous between very humid, less humid, very humid, less humid. During very humid period, you favor the weathering. During less humid, you favor more physical erosion. And this is based on this alternation of two periods that you can generate the system. So it means that the terraces and the pediment have the same type of shaping, more or less continuous uplift and change in the climate with different climate changes for the terraces, and for the pediment you need to have a lateritic period and a period of physical erosion. And in both cases, what is important is to date. And what is great is that now, both for terraces and for weathering and related landforms, we have all the techniques available, but in all the cases, you have to know what you do. You cannot pick a sample and to send it to the lab. You have to think about what it is, because it's expensive. There are few people doing that, but by the end, it's very successful. Okay, so that's it. Yeah, yeah, it's 4 minutes after 6, so that's fine. So it means that you will be free soon. So again, I apologize, to talk about that without asking you question, but you asked me some at the beginning, and again I repeat, if you want a specific discussion on one aspect or another one, we can manage to have a specific meeting, 1, 2, or 3. It's up to you if you want to discuss on a specific topic. So I hope, and this is something that I would like to know, and probably I will send you a mail for that, is to know if it was difficult for you to follow this course, this talk. So this is something that is important for me to know, okay, for the next step. So for example, I would like to know if you are familiar with, for example, the physical processes of erosion, the chemical processes of erosion. If you know, if for you it was something that you already known, or if it is really something new. Okay, and this is a point that is important. But we will send you a mail, and we will organize to do a kind of analysis of your knowledge with Milita. Okay, so if you have a specific question, I can answer.
Francois?
Yeah.
Lucas here. You had mentioned that they were able to date the saprolite through magnetic stratigraphy in Scotland, right?
Yeah.
Oh yeah. Do you happen to know or have the?
Yeah, this is a paper by a guy called Hall. It was published in Nature and PalCube. Okay, so I can. You send me a mail.
Yeah, thank you.
And I will send you the reference if you are interested in. It's dated Marcy.
François, I think Marine had a question as well in the chat.
Yeah, I asked the question on the chat, but I think you answered it afterwards. But it was to know if pediplains were considered as surface structural or surface.
So the concept of surface structural is a very French concept, and so the surface structural is when you get a lithology, a boundary between two lithology cropping out. Okay, okay, and in classical geomorphology, the one that Seb was talking before, you said this is a surface structural, this is not. And okay, so what? Okay. And surface structural could be just by chance the fact that you eroded something that is softer compared to something that is harder. So it means that you have to have a process to get this surface cropping out. But you have to have a process, okay? So it's what is important, okay? So it's not by chance that the surface is cropping out, okay? You have to have a... And some planation surface can be a structural surface, but most of them cut through different lithology, okay? For example, I take an example. When you get a thick quartzitic series, and above you get schist, for example. Of course, the contrast between quartzite and schist, on one side you get something that is 99% of quartz, that is mostly impossible to weather, okay? And on the other hand, you get something that is schist made of clay that could be fully transformed in terms of kaolinite, okay? So just by weathering, what will be the next is that you will get a relief corresponding to the quartzites, and all the schist will be removed by chemical and physical erosion. And this was considered by the French geomorphologists as a surface structural. But it means nothing. It's just a lithological contrast that record a different weathering and physical erosion. And it's what is important to understand is why it is a surface cropping out. Is that okay?
Okay. Yes, but so the pediplane has the same age all over.
The pediplane is the same than the pediment. It's just a question of size.
Yes, but it has the same age all over the surface.
No. It's the main problem. So it's that those surfaces could be polygenic. Okay, so for example, you can start to get them. For example, the one in the Bushman land is clearly around 80, 70 million years old. Okay, so it's a nice weathering surface, but it's full of diamond. It's what is interesting is that on the top it's full of diamond because you get a bypassing river system on this platform, okay? But it's bypassing, so it's why you get bypass, and it's why, because you get bypass, that you get a concentration of the dense particle. It's why you have diamond, is that there are a lot of sands crossing over that surface, okay? And only the dense particle, diamonds, gold, and so on, were left on the surface. It's what understanding a bypass is so important, is that you get a physical segregation of the particle based on the density, okay? And at that time, you reshape the surface, okay? And later on, you change the climate after this deposition, and you weathered again the surface. So it means that you have to integrate that the surface could be long-lasting surfaces. So it means that you have a paroxysm of planation, that is a major humid period, And later on, you can get wind action, you can get moderate reverse drilling, you can get fluvial crossing on. So it's a quite complex history. This is not simple, okay? And keep in mind that you never stop the erosion of a landform. Okay. Even slow, you have all the time wind, you have all the time a process that will rework the landform.
Okay, thank you.
If so, Seb?
Yes, well, first I want to say thank you, François, for the endurance. Well done, big day, and to all the participants as well. These are quite long days. We recognize that also as teachers.
So we have to have a virtual beer.
Yeah, we should. Unfortunately, I have another meeting coming up now. No, I would just say, you know, to the students, it's probably difficult, like any lecture, to stay in front of a screen and listen. But I would try to, I don't know, communicate some enthusiasm. This is really what you hear is going to be very varied. There's going to be a lot of variations, and it's very broad. And I can only tell you, it's an incredible, cool thing to hear all of this now. You know, the stories that François just told. Try to remember, try to fix it in your mind, try to be interested, because all of this will pop up again and again in front of you in the next 20, 30, 40 years as you will be a geologist. And it's really good when you are a geologist in the future and you remember this course and the stuff you've heard about, because then it rings a bell and it helps you a lot. So I can only say I think it's a lot of effort. We are aware of that, but I think it's really worth this effort. And so also during your PhD, we hope this kind of mind opening will be beneficial for you.
And again, I repeat what I said. On the field, it would be much more easier. So the regular way now to do things on the field is to go to the bar, to have a drink and to chat and to follow discussion about, and with Seb and Jean, yes, you said that, but maybe I do not necessarily agree with that. Maybe blah, blah, blah. And for you, that is very interesting to participate or to be part of this discussion, disagreement, or too fast conclusion. So that's really a point. And again, it's why I repeat, because of the COVID, what I propose you is to have a separate discussion. So if you have points that you don't understand, please do not hesitate to ask. And we will try to manage a kind of forum on the website, where you can be able to now you have the address of each other, to share your interrogation between the different ESR. And again, I repeat, if you get troubles, or if there are points that for me are obvious, but for you not, or please do not hesitate. We can organize the discussion at 5, 1, 2, 5, 10 people. So that's
yeah. On this point, it's good to, you know, it's also normal if you don't have questions now. Many of those things are sometimes new, but you can ponder them, you can think about them, and maybe a question comes later. So don't hesitate to ask later, or when we meet on the field. You know, in Spain, or in the future of this project. Really, I think our role is to help you find something new, and Francois is a living library. There's so much knowledge, so much papers. I think that's really crux. It's really crucial that you try to get the most of all this knowledge already processed once, you know, and then it's up to you to process it. But there's so much papers read. There's so much you can read in 1 year, but you can imagine in a career how much papers you read. So this is a chance for you. It's the difference between learning by yourself and learning with someone, is that someone already processed things for you and can point you directly to the things. So I think it's really a chance. Anyway, we need to stop.